Here's a number that determines whether you exist. 299,792, 458 meters per second, the speed of light. Change this number even slightly, and atoms can't form, stars can't shine, and the universe becomes a lifeless void. But here's what keeps physicists awake at night. We have no idea why light travels at this exact speed. It's not derived from anything more fundamental, it simply is. And that seemingly arbitrary number might hold the key to the deepest mystery in physics. Why does our universe exist at all? If you're fascinated by the fundamental mysteries of our cosmos and want to explore the deepest questions in physics, make sure to subscribe to this channel and give this video a thumbs up. And one quick question, if you could travel at the speed of light, where's the first place you'd go? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. Let's start with a simple question. How do we even know what the speed of light is? The story begins in 1676 with a Danish astronomer named Ole Rømer. He was studying Jupiter's moon Io, timing its eclipses as it passed behind the giant planet. He noticed something odd. The eclipses happened earlier when Earth was closer to Jupiter and later when Earth was farther away. Rømer realized he was seeing the effect of light's finite speed. When Earth was farther from Jupiter, light had to travel a greater distance to reach us, causing a delay. From these observations, he calculated that light travels at about 220,000 kilometers per second, remarkably close to the actual value considering his primitive instruments. The next breakthrough came from James Clerk Maxwell in the 1860s. While working on his equations for electricity and magnetism, he discovered something astonishing. His equations predicted that electromagnetic waves should exist and they should travel at a specific speed. When he calculated this speed using measurements of electric and magnetic forces, he got exactly the speed of light. This wasn't a coincidence, it was a revelation. Light is an electromagnetic wave. The speed of light emerges naturally from the properties of electric and magnetic fields. It's like discovering that the speed of sound isn't arbitrary but comes from the properties of air molecules. But unlike sound, which needs a medium, light travels through the vacuum of space itself. Albert Michelson and Edward Morley tried to measure Earth's motion through the luminiferous aether. The medium scientists thought carried light waves. Their experiment, performed in 1887, failed spectacularly. No matter which direction Earth moved in its orbit, light always traveled at the same speed. This null result was one of the most important failed experiments in history. Einstein solved the puzzle in 1905 with special relativity. He made a radical proposition. The speed of light in vacuum is the same for all observers, regardless of their motion. If you're standing still or racing toward a light beam at half the speed of light, you'll still measure that beam moving at exactly c. 299,792.458 kilometers per second. This constancy of light speed has profound consequences. It means space and time aren't fixed stages where events happen. They're flexible, dynamic aspects of space-time that bend and stretch depending on your motion. The faster you move through space, the slower you move through time. At the speed of light, time stops entirely. But why is the speed of light what it is? To understand this, we need to dive into the fundamental structure of space itself. According to quantum field theory, empty space isn't empty. It's filled with quantum fields, invisible entities that permeate all of space. The electromagnetic field is one of these, and light is a ripple in this field. The speed of light is determined by two properties of the vacuum, its electric permittivity and magnetic permeability. These tell us how strongly the vacuum responds to electric and magnetic fields. Think of space as a cosmic jello. These properties determine how stiff the jello is, which determines how fast waves can travel through it. but this just pushes the question back a level. Why does the vacuum have these specific properties? This is where things get really interesting. Some physicists think the speed of light might be different in other regions of the universe, or might have changed over cosmic time. If true, this would revolutionize our understanding of physics. João Magejo and Andreas Albrecht proposed the varying speed of light theory in 1998. They suggested that light might have traveled faster in the early universe, solving several cosmological puzzles, including the horizon problem, how distant regions of the universe have the same temperature despite being too far apart for light to travel between them. The Webb Space Telescope has been searching for evidence of varying fundamental constants by looking at the most distant galaxies. Light from these galaxies has been traveling for over 13 billion years. If the speed of light or other constants have changed, we should see differences in how atoms behaved in the early universe. So far, the constraints are tight. If the speed of light has changed, it's by less than 1 part in a billion. But there's another way to think about why light has its particular speed. The anthropic principle suggests that we observe this value because it's compatible with our existence. If the speed of light were significantly different, atoms might not be stable, stars might not shine, and life as we know it couldn't exist. We're here to ask the question only because the speed of light has the value it does. Consider what would happen if light traveled much faster. The fine structure constant, which depends on the speed of light, would change. This constant determines the strength of electromagnetic interactions in atoms. Make it too large, and electrons would spiral into nuclei. Make it too small, and atoms couldn't bond to form molecules. Chemistry itself depends on light having its exact speed. The speed of light also determines the rate of nuclear fusion in stars. If light were faster, the electromagnetic force would be stronger relative to gravity. Stars would burn their fuel too quickly, exhausting themselves in millions rather than billions of years. There wouldn't be enough time for planets to form and life to evolve. Our sun would have burned out long before Earth could develop complex organisms. Even more fundamentally, the speed of light sets the scale for causality itself. It determines the maximum rate at which cause and effect can propagate through space. If this speed were infinite, the entire universe would be causally connected instantly. There would be no locality. Everything would affect everything else immediately. The universe would be a chaotic mess, where prediction and science itself would be impossible. The relationship between light speed and cosmic evolution is profound. Galaxies form through gravitational collapse, but radiation pressure from stars pushes back against gravity. The balance between these forces, which depends on the speed of light, determines how galaxies evolve. Speaking of galaxy evolution, if you want to see what will happen when our Milky Way collides with the Andromeda galaxy in 4 billion years, a cosmic dance where the speed of light will determine how we see this spectacular event unfold. Check out my video called "What Will Happen When the Milky Way Collides with Andromeda?" The link is in the description and on the card above. Recent experiments have pushed our measurement precision to extraordinary levels. Using optical atomic clocks, scientists can now measure frequencies to 18 decimal places. These measurements confirm that the speed of light hasn't changed by even 1 part in 10 to the 18 over the past few years. If it's changing, it's doing so incredibly slowly. But what if the speed of light isn't fundamental at all? Some theories suggest that what we call the speed of light is actually an emergent property of something deeper. Loop quantum gravity proposes that space-time itself is made of tiny, discrete loops at the Planck scale. The speed of light might emerge from how these loops connect and interact, like how the speed of sound emerges from molecular collisions. String theory offers another perspective. In this framework, our three-dimensional space might be a membrane floating in higher dimensions. The speed of light in our universe might be determined by the tension of this membrane. and how it's embedded in the higher dimensional space. Different membranes might have different speeds of light. The most precise measurement of light speed came from defining it. In 1983, the international science community did something remarkable. They defined the meter in terms of the speed of light. 1 meter is now the distance light travels in vacuum in 1,299,792,458 of a second. The speed of light is now exactly 299,792,458 meters per second by definition. This might seem like cheating, but it reflects a deep truth. The speed of light is more fundamental than our human-created units of distance and time. We're not measuring the speed of light in meters per second, we're defining meters and seconds in terms of light speed. The universe doesn't care about our units, it operates on its own fundamental scales. Quantum mechanics adds another layer to the mystery. Virtual particles constantly pop in and out of existence in the quantum vacuum. These particles should affect how light travels, like how air affects sound. Indeed, quantum field theory predicts that the vacuum should be filled with infinite energy, which should make the speed of light zero or infinite. The fact that it's neither is one of the biggest puzzles in physics. This is called the cosmological constant problem, and it might be related to why light has its particular speed. The vacuum energy we observe is 120 orders of magnitude smaller than what quantum mechanics predicts. This incredible fine-tuning might be connected to the speed of light and other fundamental constants in ways we don't yet understand. The speed of light also plays a crucial role in quantum entanglement, what Einstein famously called spooky action at a distance. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. But here's the key. No information can be transmitted through entanglement faster than light. The universe seems to have a built-in protection mechanism preventing faster-than-light communication. This cosmic speed limit isn't just about light, it's about information itself. Whether it's light, gravitational waves, or any form of cause and effect, nothing can propagate faster than c. This suggests that the speed of light is really the speed of causality, the maximum rate at which one event can influence another. It's the universe's fundamental clock speed, like the processor speed of a cosmic computer. Recent discoveries from LIGO and Virgo gravitational wave detectors have confirmed that gravity also travels at the speed of light. When two neutron stars collided in 2017, both gravitational waves and light from the event reached Earth, having traveled 130 million light-years. They arrived within seconds of each other, confirming Einstein's prediction that gravity and light travel at the same cosmic speed limit. But why should gravity and light travel at the same speed? They're completely different phenomena. One is electromagnetic radiation, the other is the curvature of space-time itself. The fact that they share the same speed suggests something profound about the nature of space and time. Perhaps this speed is a property of space-time itself, not of the things moving through it. Paul Dirac, one of the founders of quantum mechanics, noticed something strange about fundamental constants. When he calculated the ratio of the electromagnetic force to gravity, he got a huge number, about 10 to the 40. Curiously, this is roughly the same as the age of the universe expressed in atomic units. Dirac wondered if this was coincidence or if fundamental constants might change as the universe ages. If Dirac was right, the speed of light might be slowly changing as the universe evolves. Some measurements of distant quasars hint at tiny variations in the fine structure, constant over billions of years, which would imply changes in light speed. But the evidence is controversial, and most physicists think the constants are truly constant. The multiverse theory offers another perspective on why light has its specific speed. If our universe is one of countless others, each with different fundamental constants, then we naturally find ourselves in one where the constants allow atoms, stars, and life to exist. The speed of light in other universes might be radically different, creating worlds we can barely imagine. In some hypothetical universes with faster light, electromagnetic forces would dominate. Atoms might be enormous, or they might not form at all. In universes with slower light, gravity might dominate, causing everything to collapse into black holes. Our universe might occupy a sweet spot where the forces are balanced just right for complexity to emerge. The holographic principle suggests that our three-dimensional universe might be encoded on a two-dimensional surface, like a hologram. In this view, the speed of light might be related to the rate at which information can be processed on this holographic boundary. We're living inside a cosmic hologram, and light speed is the refresh rate of the projection. Recent experiments have pushed the boundaries of manipulating light speed. Scientists have slowed light down to walking speed by passing it through ultra-cold atoms. They've even stopped light completely, storing its information in atomic states. But this isn't changing the fundamental speed of light. It's just light interacting with matter. In the vacuum between atoms, light still races along at its universal constant speed. The question of why light has its specific speed might be connected to the deepest mystery in physics, quantum gravity. We have quantum mechanics describing the very small and general relativity describing the very large, but they're incompatible. The speed of light appears in both theories, suggesting it might be the key to unifying them. Some quantum gravity theories predict that space-time itself becomes grainy at the Planck scale, 10 to the negative 35 meters. At this scale, the smooth space-time of Einstein might break down into discrete units. The speed of light might emerge from how disturbances propagate through this quantum foam, like how sound emerges from air molecules. The Large Hadron Collider has searched for signs of extra dimensions by looking for microscopic black holes and missing energy. If extra dimensions exist, they might affect how gravity propagates compared to light. So far, no deviations have been found, confirming that both gravity and light respect the same cosmic speed limit up to the highest energies we can test. Cosmic rays offer another test. These high-energy particles have traveled millions of light-years to reach Earth. If the speed of light varied with energy, different energy photons would arrive at different times. The Fermi Space Telescope has monitored gamma-ray bursts billions of light-years away and found that photons of vastly different energies arrive simultaneously, confirming light speed's constancy to extraordinary precision. The constancy of light speed has profound implications for our understanding of time. In Einstein's relativity, time and space are intertwined into space-time, and the speed of light is the conversion factor between them. 1 second of time equals 299,792.458 kilometers of space. When you sit still, you're traveling through time at the speed of light. When you move through space, you're diverting some of that speed from time to space. This is why time dilation occurs. GPS satellites orbiting Earth experience time slightly faster than we do on the surface because they're in weaker gravity and moving relative to us. Without corrections for these relativistic effects, all dependent on the speed of light, GPS would accumulate errors of about 10 kilometers per day. The speed of light isn't just theoretical, it's essential for the technology in your pocket. But here's a mind-bending thought. What if the speed of light is infinite and it's space and time that are emergent? Some theories propose that what we perceive as finite light speed is actually a consequence of how our consciousness processes information. We're embedded in space-time, so we can't see the underlying reality where information transfer might be instantaneous. The discovery of dark energy in 1998 added another piece to the puzzle. The universe's expansion is accelerating, driven by a mysterious force that makes up about 68% of the universe's energy density. Some physicists wonder if dark energy might be related to the speed of light. Perhaps both are aspects of the vacuum's fundamental properties. String theory suggests our universe might be a three-dimensional brain floating in higher dimensional space. The speed of light on our brain might be determined by how it's oriented in the higher dimensions. If our brain is moving or rotating through the higher dimensional space, it might cause the speed of light to vary over cosmic time or in different directions. Recent observations from the Dark Energy Survey have mapped millions of galaxies to unprecedented precision. By studying how light from distant galaxies is bent by intervening matter, gravitational lensing, astronomers can test whether light speed has remained constant over billions of years. So far, no variations have been detected, but the search continues with ever-increasing sensitivity. The speed of light also determines the size of atoms. The Bohr radius, the typical size of a hydrogen atom, depends on the speed of light through the fine structure constant. If light were faster, atoms would be smaller. If it was slower, atoms would be larger. The very scale of matter, from DNA molecules to the human body, is set by light's speed. This connects to a deeper question: why is the universe so big? Observable universe has a radius of about 46 billion light-years, containing over 2 trillion galaxies. This vast size is directly related to the speed of light and the age of the universe. If light were faster, we could see farther. If it was slower, our observable universe would be smaller. The Planck satellite mapped the cosmic microwave background, the afterglow of the Big Bang, with extraordinary precision. Hidden in its data might be clues about whether fundamental constants like light speed have changed. Some anomalies, like the axis of evil, by an unexpected alignment of temperature fluctuations, might hint at new physics beyond our standard models. Quantum field theory reveals that the speed of light is related to the vacuum's resistance to electromagnetic fields. Just as sound speed depends on air's density and elasticity, light speed depends on the vacuum's electromagnetic properties. But unlike air, which is made of atoms, the vacuum's properties emerge from quantum fields themselves, a kind of circular definition that points to deeper mysteries. Scientists have proposed various experiments to test whether light speed might vary. The PVLS experiment in Italy looks for vacuum birefringence, whether strong magnetic fields can affect light propagation. The GRB Alpha satellite monitors gamma-ray bursts for energy-dependent arrival times. These experiments push the boundaries of our understanding, searching for cracks in the foundation of physics. The relationship between light speed and entropy is particularly intriguing. Information theory tells us that information can't be created or destroyed, only transformed. The speed of light limits how fast information can spread, which affects how entropy increases. Some physicists suggest that the second law of thermodynamics, entropy always increases, might be fundamentally connected to the finite speed of light. Black holes provide the ultimate test of light speed significance. At the event horizon, space-time is so warped that light itself can't escape. The size of a black hole's event horizon is directly proportional to its mass and depends on the speed of light. If light speed were different, black holes would be different sizes, affecting how galaxies form and evolve. Recent simulations of the early universe suggest that the speed of light plays a crucial role in structure formation. After the Big Bang, tiny quantum fluctuations grew into the cosmic web of galaxies we see today. The rate of this growth depends on how fast different regions can communicate, limited by light speed. A different speed would result in a completely different cosmic architecture. The speed of light even affects the stability of matter itself. Neutron stars, the densest objects besides black holes, exist in a delicate balance between gravity trying to crush them and neutron degeneracy pressure pushing back. This balance depends critically on the speed of light through relativistic effects. If light speed were different, neutron stars might not exist, or they might collapse immediately into black holes. One of the most profound connections is between light speed and the uncertainty principle. Heisenberg showed that you can't simultaneously know a particle's exact position and momentum. This uncertainty is fundamentally linked to the speed of light. It sets the scale at which quantum effects become important. Change light speed, and you change the boundary between the quantum and classical worlds. The Alpha experiment at CERN has been studying antimatter to see if it respects the same laws as matter. They've confirmed that antihydrogen atoms emit and absorb light at exactly the same frequencies as regular hydrogen. This means the speed of light is the same for antimatter, ruling out some exotic theories where antimatter might experience different fundamental constants. But what about tachyons, hypothetical particles that travel faster than light? If they exist, they would experience time backward and could violate causality. Most physicists believe tachyons are impossible, but some string theory models predict tachyonic states. The absence of observed tachyons might be another clue about why the universe has chosen this particular speed limit. The cosmic speed limit also determines the maximum density of information in space. The Bekenstein bound states that a region of space can only contain a finite amount of information proportional to its surface area rather than volume. This bound depends on the speed of light and suggests that space itself might be fundamentally digital rather than continuous. Recent advances in metamaterials have created substances with negative refractive indices where light appears to travel backward. These materials don't violate relativity. Light still travels at c in the vacuum between atoms, but they show how the effective speed of light in materials can be manipulated, leading to possibilities like invisibility cloaks and superlenses. The speed of light also sets fundamental limits on computation. The Margolis-Levitin theorem states that the maximum rate of computation is proportional to energy divided by Planck's constant. Since energy and mass are related by E equals mc squared, the speed of light ultimately limits how fast any computer, biological or artificial, can process information. This computational limit might explain why the universe seems to have the constants it does. If the universe is computing its own evolution, it needs consistent rules that allow stable computation. The speed of light might be set at a value that maximizes the universe's computational capacity while maintaining stability and allowing complex structures to form. The relationship between light speed and consciousness is particularly intriguing. Our brains process information using electrical signals that propagate much slower than light, about 100 meters per second. But the electromagnetic fields generated by neural activity propagate at light speed. Some theories of consciousness propose that these fields play a crucial role in binding our experiences into unified awareness. Observations of pulsars, rapidly rotating neutron stars, provide some of the most stringent tests of light speed constancy. The Hulse-Taylor binary pulsar has been monitored for decades, and its orbital decay matches Einstein's predictions to better than 0.2%. Any variation in light speed would show up as deviations from these predictions. The cosmic web, the largest structure in the universe, owes its existence to the finite speed of light. Galaxies are connected by filaments of dark matter and gas with vast voids between them. This structure formed because gravity could only pull matter together as fast as light speed allowed information about mass distributions to propagate. An infinite light speed would have created a very different universe. The speed of light also plays a crucial role in the universe's transparency. After the Big Bang, the universe was opaque to light for about 380,000 years. Then, as it cooled enough for atoms to form, light could suddenly travel freely. This moment, called recombination, happened when the universe became cool enough that photons traveled at sea without constantly scattering off free electrons. Some of the most exotic objects in the universe owe their properties to light speed. Quasars, powered by supermassive black holes, can outshine entire galaxies. The efficiency of converting matter to energy in their accretion disks depends on relativistic effects. Jets from these objects can appear to travel faster than light due to projection effects, though they actually respect the cosmic speed limit. The search for quantum gravity has led to proposals that space and time themselves might be emergent from something more fundamental. In these theories, the speed of light might emerge from the dynamics of quantum information. Just as temperature emerges from molecular motion, light speed might emerge from the atoms of space-time itself. The Pioneer anomaly provided an unexpected test of our understanding of light speed. The Pioneer 10 and 11 spacecraft, launched in the 1970s, showed tiny, unexplained accelerations toward the Sun. For years, physicists wondered if this indicated new physics or variations in fundamental constants. Eventually, they traced it to thermal radiation from the spacecraft's power sources, a relief for standard physics, but a reminder of how precisely we must account for light's behavior. One fascinating possibility is that the speed of light might be related to the number of dimensions in our universe. We experience 3 spatial dimensions plus time, but string theory suggests there might be 6 or 7 additional dimensions curled up at microscopic scales. The speed of light in our familiar dimensions might be determined by how these extra dimensions are compactified. The cosmic neutrino background, relic neutrinos from just seconds after the Big Bang, carries information about the early universe when temperatures exceeded 1 trillion degrees. These ghostly particles travel at nearly the speed of light, and their detection would provide another test of whether fundamental constants have changed over cosmic time. The proposed Ptolemy experiment might finally catch these elusive messengers. Recent observations of white dwarf stars have placed stringent limits on any variation in the speed of light. White dwarfs cool at predictable rates that depend on fundamental constants. By studying white dwarfs in globular clusters of known ages, astronomers have shown that the speed of light hasn't changed by more than 1 part in 10 billion over the past 10 billion years. The relationship between light speed and mass is encoded in Einstein's famous equation, but it goes deeper. The Higgs field, which gives particles their mass, permeates all of space. The speed of light might be related to how particles interact with this field. Massless particles like photons don't interact with the Higgs field and always travel at c. Massive particles interact with it and always travel slower than c. Quantum chromodynamics, the theory of the strong force that binds quarks into protons and neutrons, reveals another aspect of light speed's importance. Inside protons, quarks and gluons move at significant fractions of light speed. The proton's properties, including its size and magnetic moment, depend critically on relativistic effects. Change the speed of light, and you change the very nature of matter's building blocks. The speed of light also determines the range of fundamental forces. The electromagnetic and gravitational forces have infinite range because photons and gravitons are massless and travel at c. The weak nuclear force has a short range because its carriers, the W and Z bosons, are massive. This difference, ultimately tied to light speed, explains why atoms exist and why the sun shines. Cosmological observations suggest our universe underwent inflation, a period of exponential expansion in its first fraction of a second. During inflation, space itself expanded faster than light. This isn't a contradiction because it's space expanding, not objects moving through space. The speed of light limits motion through space, not the expansion of space itself. The holographic principle has led to fascinating connections between light speed and black hole thermodynamics. The maximum entropy of a region is proportional to its surface area, not volume, and this area is measured in units of the Planck length squared, a quantity that depends on light speed. This suggests that information, entropy, and light speed are fundamentally intertwined. Recent experiments with ultra-cold atoms have created analogues of cosmic phenomena in the laboratory. By carefully controlling atomic interactions, scientists can create systems where sound plays the role of light, with its own speed limit. These experiments help us understand how horizons form and how the speed of light shapes the causal structure of space-time. The speed of light might even be connected to why time flows forward. The thermodynamic arrow of time, the fact that entropy increases, requires that information can only propagate at finite speed. If light speed were infinite, cause and effect could be instantaneous everywhere, potentially allowing entropy to decrease and time to flow backward. Observations of cosmic rays have revealed particles with energies that challenge our understanding. The GZK cutoff predicts that cosmic ray protons above a certain energy should interact with the cosmic microwave background and lose energy. The fact that we observe this cutoff confirms that these particles respect the speed of light limit even at the highest energies in the universe. The relationship between light speed and the vacuum catastrophe, the enormous discrepancy between observed and predicted vacuum energy, remains one of physics' greatest mysteries. Some theorists suggest that understanding why the vacuum energy is so small might also explain why light has its particular speed. Both might emerge from a deeper theory we haven't discovered yet. Gravitational wave astronomy has opened a new window on the universe. LIGO and Virgo have detected dozens of black hole mergers, each confirming that gravitational waves travel at light speed. Future detectors like LISA will probe different frequencies, potentially revealing whether this speed limit holds across all scales and conditions. The quantum vacuum isn't empty but seethes with virtual particles popping in and out of existence. These quantum fluctuations should affect how light propagates, potentially causing the speed to vary slightly depending on wavelength, an effect called vacuum dispersion. The fact that we don't observe this dispersion, even for light that has traveled billions of years, places incredible constraints on quantum gravity theories. One of the most profound questions is whether the speed of light is truly universal or just locally constant. In regions of extreme space-time curvature, like near black holes or during the universe's first moments, the effective speed of light might differ from what we measure in our relatively flat space-time. The Event Horizon Telescope's observations of black holes are beginning to probe these extreme regimes. The speed of light connects to the deepest questions about free will and determinism. Because information can't travel faster than light, there's always a delay between cause and effect. This light cone structure of space-time might provide the elbow room needed for quantum indeterminacy and possibly free will to exist. Without this finite speed, the universe might be completely deterministic. Recent discoveries about quantum entanglement have revealed that while no information can be transmitted faster than light, correlations can be established instantaneously. This has led to quantum technologies like quantum cryptography and quantum computing. The interplay between quantum non-locality and relativistic locality, both governed by light speed, is reshaping our understanding of information and computation. The cosmic web's filamentary structure results from the interplay between dark matter's gravity and ordinary matter's pressure, mediated by photons traveling at light speed. Simulations show that different light speeds would create vastly different cosmic structures. Our universe's particular web pattern, with its mix of clusters, filaments, and voids, depends critically on light having its observed speed. Primordial black holes, possibly formed in the universe's first second, offer another test of light speed constancy. If these objects exist, their properties depend on the fundamental constants at the time of their formation. Detecting primordial black holes through gravitational lensing or gravitational waves could tell us whether light speed has remained constant since the universe's earliest moments. The relationship between light speed and the arrow of time becomes even more intriguing when we consider black holes. At the event horizon, space and time effectively switch roles. Inside the horizon, the radial direction becomes time-like. You must move toward the singularity just as you must move toward the future. This intimate connection between light speed and time's direction shapes the causal structure of space-time. Laboratory experiments continue to push the boundaries of our understanding. Optical lattice clocks can now measure time to a precision of 1 part in 10 to the 19, so accurate they can detect the gravitational time dilation from raising the clock by just 1 centimeter. These incredible instruments could detect any variation in fundamental constants, including light speed, with unprecedented sensitivity. The speed of light also governs the maximum size of gravitationally bound structures. Galaxy clusters, the largest bound objects in the universe, have sizes limited by how fast gravity can communicate across them. If light speed were different, the hierarchy of cosmic structures, from solar systems to galaxies to clusters, would be entirely different. String theory's landscape of possible universes suggests that different regions of a larger multiverse might have different light speeds. These regions would be causally disconnected, unable to communicate with each other. We might live in a tiny bubble with our particular light speed, surrounded by regions with wildly different physics that we can never observe or visit. The relationship between light speed and consciousness remains one of the most speculative but fascinating areas of research. Some theories propose that consciousness requires a certain rate of information integration, which depends on the speed of neural signals and electromagnetic fields in the brain. The specific value of light speed might be necessary for consciousness, as we know it to exist. Observations of fast radio bursts, mysterious millisecond pulses from distant galaxies, have provided new tests of light speed constancy. These bursts travel billions of light years, and any variation in light speed, with frequency, would spread out their arrival times. The fact that they arrive as sharp pulses confirms light speed's constancy to extraordinary precision across cosmic distances. The speed of light might be connected to the universe's information content. If the universe is fundamentally computational, processing its own evolution, then light speed sets the clock rate of this cosmic computer. The total information content of the observable universe, estimated at 10 to the 120 bits, depends directly on light speed through the holographic bound. Recent advances in understanding emergent gravity suggest that space-time and gravity might not be fundamental, but emerge from quantum entanglement. In these theories, the speed of light would emerge from the rate at which quantum information can flow through the entanglement network. This would make light speed a derived quantity rather than a fundamental constant. The discovery of time crystals, structures that repeat in time rather than space, has opened new perspectives on fundamental constants. These quantum systems exhibit periodic behavior without consuming energy, challenging our understanding of time itself. The speed of light plays a crucial role in determining the possible frequencies and stability of these exotic states of matter. Astronomical observations of gamma-ray bursts have revealed some of the most energetic events in the universe. When massive stars collapse or neutron stars merge, they can briefly outshine entire galaxies. The fact that gamma rays of vastly different energies arrive simultaneously after traveling billions of light years confirms that light speed doesn't depend on photon energy to at least 1 part in 10 to the 17. The relationship between light speed and quantum tunneling reveals deep connections in physics. When particles tunnel through barriers they classically shouldn't be able to cross, the process isn't instantaneous. Recent experiments have shown that tunneling time is limited by light speed, maintaining causality even in the quantum realm. This preserves the logical structure of cause and effect at the smallest scales. Dark matter, which makes up 85% of the universe's matter, might interact with ordinary matter through forces other than gravity. If dark matter particles exist, they must respect the speed of light limit. Experiments deep underground search for these elusive particles, and their non-detection places constraints on new forces that might modify how we understand fundamental constants. The cosmic microwave background's near-perfect uniformity tells us that the early universe reached thermal equilibrium. This required different regions to communicate, which they could only do at light speed. The horizon problem, how regions too far apart to have ever communicated have the same temperature, led to inflation theory. The speed of light is central to this fundamental puzzle about our universe's initial conditions. Recent observations of neutron star mergers have provided a cosmic laboratory for extreme physics. When two neutron stars spiral together and merge, they create conditions impossible to replicate on Earth. Densities exceeding atomic nuclei and magnetic fields trillions of times stronger than Earth's. The gravitational waves and light from these events travel at the same speed across millions of light-years, confirming Einstein's prediction with extraordinary precision. The speed of light might be related to the dimensionality of space itself. In hypothetical, two-dimensional or four-dimensional spaces, electromagnetic waves would propagate differently. The fact that light spreads out as 1 over distance squared in our universe is intimately connected to space having exactly 3 dimensions. This connection suggests deep relationships between geometry and fundamental constants. Quantum field theory, in curved space-time, predicts that accelerating observers see a thermal bath of particles, the Unruh effect. The temperature of this bath depends on acceleration and the speed of light. This connects light speed to thermodynamics and suggests that what we call empty space depends on our state of motion, all governed by the cosmic speed limit. The possibility of warp drives, space-time geometries that could allow effective faster-than-light travel without locally exceeding light speed, depends critically on exotic matter with negative energy density. While general relativity allows such solutions, they require conditions that might be forbidden by quantum effects. The speed of light limit might be protected by deep principles we don't yet understand. Observations of the cosmic web have revealed that galaxies aren't randomly distributed but form a vast network of filaments and voids. This structure formed through gravitational instability, with the growth rate determined by how fast gravity can communicate at light speed. Computer simulations with different light speeds produce completely different cosmic architectures, suggesting our universe's structure is fine-tuned by this fundamental constant. The relationship between light speed and the stability of atoms goes beyond simple electromagnetic forces. Relativistic effects become important for inner electrons in heavy atoms, affecting their chemistry. Gold's yellow color, Mercury's liquid state at room temperature, and lead's resistance to corrosion all result from relativistic effects. Change light speed, and the periodic table would be unrecognizable. Recent experiments with Bose-Einstein condensates have created analogues of black holes, where sound plays the role of light. These dumb holes trap sound waves, just as black holes trap light. By studying how phonons behave near these acoustic horizons, physicists gain insights into how the speed of light shapes the causal structure of spacetime and the nature of Hawking radiation. The speed of light determines the maximum frequency of electromagnetic radiation. The Planck frequency, about 10 to the 43 Hz, represents the highest possible frequency before quantum gravitational effects dominate. This sets an upper limit on the energy of photons and the resolution with which we can probe spacetime. Light speed thus determines the fundamental graininess of reality. Cosmic inflation theory suggests that quantum fluctuations during the universe's exponential expansion became the seeds of all cosmic structure. The amplitude and scale of these fluctuations depend on the relationship between the expansion rate and light speed. Our existence in a universe with galaxies, stars, and planets might require light speed to have its specific value during inflation. The search for variations in fundamental constants has led to studies of the Oklo natural nuclear reactor in Gabon, Africa. 2 billion years ago, natural uranium concentrations were high enough to sustain nuclear fission reactions. By analyzing the isotope ratios in these ancient reactor zones, scientists can test whether nuclear physics, and by extension the speed of light, has remained constant over geological time. The results confirm stability to extraordinary precision. One of the most profound connections is between light speed and the nature of space-time itself. In loop quantum gravity, space consists of tiny loops at the Planck scale, and the speed of light emerges from how disturbances propagate through this quantum foam. Different arrangements of loops could yield different speeds, suggesting our observed value might result from a particular quantum geometry of space. The relationship between light speed and consciousness becomes even more intriguing when we consider integrated information theory. This theory proposes that consciousness corresponds to integrated information, how much information a system generates above its parts. The speed of light limits how quickly different parts of the brain can communicate, potentially setting fundamental constraints on consciousness and self-awareness. Recent observations of blazars, supermassive black holes shooting jets directly at Earth, have provided new tests of Lorentz invariance, the principle underlying special relativity. These jets contain particles moving at 99.9% of light speed. Any violation of Lorentz invariance would show up as energy-dependent arrival times for photons from blazar flares. None have been detected, confirming relativity to unprecedented precision. The cosmic neutrino background carries information from when the universe was just 1 second old. These relic neutrinos have been traveling at nearly light speed for 13.8 billion years. When we finally detect them, they'll provide the ultimate test of whether fundamental constants have changed since the universe's first moments. The proposed Ptolemy experiment might achieve this detection within the next decade. Quantum entanglement experiments have now demonstrated correlations between particles separated by thousands of kilometers. While no information travels faster than light in these experiments, the correlations themselves appear instantaneous. This has led to new interpretations of quantum mechanics that respect both quantum non-locality and relativistic causality, showing how nature cleverly preserves the speed of light limit while allowing quantum weirdness. The relationship between light speed and the vacuum catastrophe, why vacuum energy is 120 orders of magnitude smaller than quantum field theory predicts, might hold the key to quantum gravity. Some theories propose that the vacuum energy and light speed are related through a cosmic seesaw mechanism. As one increases, the other decreases, maintaining a delicate balance that allows our universe to exist. Observations of millisecond pulsars, neutron stars spinning hundreds of times per second, provide natural laboratories for testing fundamental physics. These cosmic lighthouses emit radio pulses with timing stability rivaling atomic clocks. Any variation in the speed of light would show up as timing irregularities. The fact that some pulsars have maintained precise timing for decades confirms light speed's constancy. The possibility of extra dimensions raises fascinating questions about light speed. In theories, with large extra dimensions, gravity might propagate through all dimensions, while other forces are confined to our three-dimensional brain. This could explain why gravity is so weak. It's diluted through extra dimensions. The speed of light in these extra dimensions might be different, affecting how gravity and other forces relate. Recent advances in metamaterials have created transformation optics, materials that bend light in ways that seem to violate common sense. While these materials can't make light exceed c in vacuum, they can create regions where light effectively stands still or moves backward. These experiments help us understand how the universal speed limit emerges from more fundamental principles. The relationship between light speed and information has led to the it from bit hypothesis, the idea that reality emerges from information. In this view, the speed of light is the maximum rate at which reality can update itself, like the refresh rate of a cosmic simulation. This connects to digital physics theories where space-time itself might be discrete rather than continuous at the smallest scales. Gravitational lensing by galaxy clusters has revealed that light paths curve around massive objects exactly as Einstein predicted. The amount of bending depends on the relationship between light speed and gravity's strength. These cosmic lenses have become tools for mapping dark matter and testing whether fundamental constants vary across the universe. So far, light speed appears truly constant. The firewall paradox in black hole physics has revealed deep tensions between quantum mechanics and general relativity. The paradox involves what happens to information falling into black holes and whether the equivalence principle breaks down at horizons. Resolving this paradox might require new understanding of how light speed, quantum mechanics, and gravity interconnect at the most fundamental level. Studies of the early universe through the cosmic microwave background have revealed tiny temperature fluctuations that seeded all cosmic structure. The angular scale of these fluctuations depends on the sound speed in the primordial plasma, which is related to light speed. The precise match between observations and theoretical predictions confirms our understanding of fundamental constants in the universe's infancy. As we approach the end of this cosmic journey, let's consider the ultimate question. Could the speed of light be different in other universes? String theory's landscape suggests 10 to the 500 possible universes, each with different fundamental constants. In this vast multiverse, light speed might range from 0 to infinity. We find ourselves in a universe with this particular value not by chance, but because it's one of the rare combinations that allows atoms, stars, galaxies, and life to exist. The anthropic principle often feels unsatisfying. It seems to explain everything and nothing simultaneously. But when combined with multiverse theories, it gains predictive power. If universes with different constants exist, we should find ourselves in the most common universe that allows observers. Some calculations suggest this predicts fundamental constants, including light speed, to within a few % of observed values. Recent breakthroughs in artificial intelligence have led to new approaches in fundamental physics. Machine learning algorithms trained on astronomical data have begun finding patterns humans missed. Some researchers wonder if AI might discover deeper principles that explain why light speed and other constants have their specific values, principles too complex or alien for human minds to grasp directly. The relationship between light speed and the ultimate fate of our universe is profound. As dark energy accelerates cosmic expansion, distant galaxies are approaching the speed of light relative to us. Eventually, they'll cross the cosmic horizon and disappear forever. The observable universe is shrinking, not in space but in content. Light speed determines how quickly we're losing cosmic contact with the wider universe. But this cosmic isolation might not be the end. Some theories propose that quantum fluctuations in the far future could create baby universes, each with potentially different constants. Our universe's death could seed countless new realities. The speed of light in these offspring universes might vary slightly, allowing cosmic evolution to explore new possibilities for complexity and life. The quest to understand light speed has driven many of humanity's greatest discoveries. From Maxwell's unification of electricity and magnetism to Einstein's relativity to quantum field theory, each breakthrough has revealed deeper layers of reality. The speed of light isn't just a number, it's a thread connecting all of physics from the quantum to the cosmic scale. Consider what we've learned. The speed of light is the speed of causality itself, the maximum rate at which cause and effect can ripple through space-time. It's the conversion factor between space and time, energy and mass. It determines the size of atoms, the luminosity of stars, the structure of galaxies, and possibly the nature of consciousness itself. Change this one constant and you change everything. Yet for all our understanding, deep mysteries remain. Why does the vacuum have the precise electromagnetic properties that give light its observed speed? Why do all massless particles travel at exactly this speed? Is the speed truly constant, or might it vary in ways too subtle for current experiments to detect? These questions drive physics forward, promising future revelations. The emotional impact of understanding light speed shouldn't be underestimated. When you look at the stars, you're seeing the past. Light that left those suns years, centuries, or millennia ago. The sun you see is 8 minutes old. The stars in Orion's belt are as they were 600 years ago. The Andromeda galaxy appears as it was 2.5 million years ago. Light speed makes the night sky a time machine. This cosmic perspective transforms how we see ourselves. Every atom in your body except hydrogen was forged in stellar furnaces. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created by stars that lived and died before our sun was born. These atoms traveled through space at speeds limited by light, taking billions of years to become part of Earth and eventually you. The speed of light connects us to the cosmos in ways both profound and practical. The GPS in your phone must account for relativistic effects. The electricity powering your home involves electrons responding to electromagnetic fields propagating at light speed. Even the chemical reactions in your cells involve electrons jumping between orbitals, governed by the fine structure constant that depends on light speed. As we develop new technologies, quantum computers, fusion reactors, gravitational wave detectors, we're probing ever deeper into the nature of reality. Each advance might bring us closer to understanding why the universe chose this particular speed limit. Perhaps one day we'll discover that 299,792.458 kilometers per second is the only value that allows reality to be mathematically consistent. Or perhaps we'll find that our universe is one note in a vast cosmic symphony, with each universe playing variations on fundamental themes. The speed of light might be like the tempo of our particular movement, arbitrary in isolation, but perfect for the melody of physics that allows complexity and consciousness to emerge. Whatever the ultimate answer, the journey of discovery continues. Every question answered reveals new mysteries. Every breakthrough deepens our awe at the elegant mathematical structure underlying reality. The speed of light, this cosmic constant that shapes everything from atoms to galaxies, reminds us that we live in a universe far stranger and more wonderful than everyday experience suggests. So the next time you turn on a light, remember that you're unleashing photons that travel at the ultimate cosmic speed limit. When you look at the stars, you're seeing the past preserved by light's finite speed. And when you ponder your place in the universe, remember that the very atoms contemplating these questions exist only because the speed of light has precisely the value it does. You are not just in the universe, you are the universe understanding itself. One insight at a time, at exactly 200 and 99,792.458 kilometers per second. If you made it this far, make sure to subscribe and give a like, and I am sure you will love this other video at the left side of the screen. What if we could travel faster than light? In this video, discover the mind-blowing science and consequences of breaking the cosmic speed limit. Explore how faster-than-light travel would transform space exploration, time, and the future of humanity. See you there.